This is our chapter on carbohydrates. So we're going to get started with our biochemistry. And so carbohydrates, or carbs, are a major source of energy in our diets. And so we've got carbon from carbohydrates, we also got hydrogen, and you have oxygen as well. And they're also called sugars, or saccharides. Glucose is a major carbohydrate. A simple carb, and we get glucose from the photosynthesis. So making a note of the photosynthesis reaction, you have carbon dioxide and water and energy going in to make a carbon compound and oxygen. But if you look at the opposite direction here, then that is kind of like a combustion reaction. And so that is what we call respiration. So we use glucose with oxygen to make energy, water, and carbon dioxide, while plants use these to make this. And so we have a great cycle of that back and forth. And so we're going to study 3 different types of carbohydrates. We're going to study monosaccharides, meaning one sugar or one saccharide, disaccharides, 2 monosaccharides together, and polysaccharides, which are more than 2. So it depends on what kind of saccharide you have. You can take a polysaccharide and you can break it down into many monosaccharides. You could take a disaccharide and break it down into 2 monosaccharides, or if you try to break apart a monosaccharide, you can't, and you're not going to break that down. And so we do this through hydrolysis, breaking these down, just like we would break esters. We have a similar process, right? There's an ester linkage, and so we have this kind of this alcohol structure that we create here. So monosaccharides consist of 3 to 7 carbon atoms, and you've got a carbonyl chain. So you have 2 different types of saccharides. You've got a saccharide with an aldehyde at the end, and we call those an aldose. And you have a saccharide with a ketone on carbon number 2, and we call that a ketose. And so you have different types of saccharides. You need to know, if you see that aldehyde on the end here, you've got an aldose, and if you see a ketone in the middle, you've got a ketose. And then you've got these hydroxyl groups. You have a hydroxyl group on every carbon, right? So this carbon has a hydroxyl, this one has a hydroxyl, and this one has a hydroxyl, right? Except for the carbonyl carbon. So you got a carbonyl carbon, and the rest of them have to have hydroxyl groups. They have to have OHs. Monosaccharides are also kind of classified by how many carbons they have. So triose would have 3 carbons, a tetrose, pentose, hexose, heptose, etc. An aldopentose would be 5 carbons with an aldehyde group on the end. A ketohexose would be 6 carbons with a ketone. So looking at some pictures of these, this has 1, 2, 3 carbons. It would be a triose, and it would be an aldehyde, so it's an aldotriose. Here we've got 1, 2, 3, 4, so it's a threose, an aldotetrose is called threose. So tetra, meaning 4 carbons. You've got a pentose, a hexose. So we're going to be getting back into those covalent names, not the main chain organic compound names. And so for monosaccharides, naming how many carbons there are is not a main chain type thing. It's not prop and but. It's going back to covalent bonding, which is a little confusing, I know. But it's tri, tetra, pent, hex. And you can see here you got a ketone hanging out in the middle, so that's a ketohexose. And so go ahead and do a quick pause and tell me if it's aldo or keto, and tetrose, pentose, or hexose. Right, so here we have an aldohexose because it has an aldehyde with an H here. So we have an aldehyde, and we have 1, 2, 3, 4, 5, 6 carbons. It's hexose. And we have 1, 2, 3, 4, 5 carbons, pentose. You got a ketone, ketopentose. That is not the name of it, but that is the classification of it. Now we have to talk about chirality. I posted a video in Canvas. It's actually a Khan Academy video, but it does a really good job of showing you exactly what chirality is. In class, we'll do a little more practice with this, and I would definitely encourage you to check out a model kit if you can from the Learning Commons, and look at that, build it yourself, and really take a look at it, because it's kind of hard to understand chirality. And so chirality means that you've got mirror images, and those mirror images are not superimposable. And we'll talk about that in just a second. But first of all, let's talk about isomers. So you should remember from our previous work, a structural isomer is isomer, meaning it has the same molecular formula. So these two things, ethanol and dimethyl ether, have the same molecular formula, 2 carbons, 6 hydrogens, and an oxygen, but they are very different molecules with very different properties, right? An alcohol has certain properties and ether has other properties, but they are the same molecular formula. So these are structural isomers. They're totally different arrangements of atoms. For example, this combination of atoms might give you propanol and a propanone, and we know that this cannot be oxidized, this can be oxidized into carboxylic acid, and so they have very different properties. If you're naming them differently, then they're different structures. But stereoisomers are a little bit different. Stereoisomers have identical molecular formulas. They're not structural isomers. They have everything bonded in the same way, but they have one difference. The difference is where the bonds are kind of pointed. So the bonds are the groups are hanging off the carbon, but they're hanging off the carbon in a different order. So it's a little hard to explain. I just kind of have to show you. And we call it chiral because the mirror images are not completely superimposable. Superimposable means if you were to put one, kind of meld one into the other, if it would be exactly the same. So looking at this, so your hands are chiral. They have the same number of digits, right? You got 4 fingers and a thumb. And so they would not, and they have them all attached in the same way. So they would not be structural isomers because they don't have the thumb attached in the middle, right? They have the thumb attached on the side, and you got the 4 fingers here in the middle. And you even have a pattern of which is the tallest finger, right, in the hand. But your hand, if you take the mirror image of your right hand, right, then you get your left hand. So if you can right now, put your hands together, okay, where your thumbs are matching. Now that your hands are mirror images of each other, right? Now try to make your hands exactly the same, like on all sides. And so what I mean by that is try to get your palm to be on the same side as your other palm, like not touching, but like superimposed, meaning like they look exactly the same standing next to each other. So if I look at but my hands kind of palm up, then my thumbs are not in the same place, right? And if I have my thumbs in the same place, then one hand is palm up and the other hand is palm down. So hopefully you're taking a second and not looking weird at the library moving your hands around. But if you can try to do this as many times as you want, taking your right or your left hand and flipping it around, and you'll find that you can never put them, like meld them into one another in exactly the same way. Like if your thumbs match, then one of your hands is palm side down and the other's palm side up. So that's not superimposed. If you have both your palms up, then your thumbs don't match, right? Or both your palms down, then your thumbs don't match. And so that's what we mean by superimposable. There's no way I can rotate my right hand to be exactly the same as like if I could like a ghost, like meld it together as my left hand, right? And so that is what chirality is. So if you were to have a molecule, draw the mirror image of it, and then try to rotate that mirror image and kind of lay it on top of or inside of the other molecule, if it would be the same, or not the same. So if it's not the same, it's non-superimposable, we call that chiral. If you can take that mirror image, flip it, and it actually is the same, we call that achiral. And so for example, if you look at this glass, right? If I were to do the mirror image, here's the mirror image of this glass. If I were to take this image and like take it into Photoshop and pull it over into this image, you wouldn't be able to tell the difference. You could superimpose this. But if I were to take one glove and try to meld it into the image of this glove, I couldn't do it, right? There's no way I can rotate the right-handed glove to fit my left hand. And so gloves are chiral. And chiral actually comes from the Greek meaning handedness. And so it comes from that same idea that a right-handed glove, if it's for real a right-handed, some gloves are either or, but for real a right-handed glove, it will never fit my left hand, ever. No matter how I rotate it and move it around, the palm side of the glove will never be the palm side of my left hand. And my shoes are also chiral. If you have ever accidentally put your shoes on the wrong feet, you know that they are not the same, right? So chiral means that that it's different, right? If you tried to like kind of lay it on top of each other. And so carbon atoms are chiral, and the easiest way to tell a chiral atom is to look at how many groups are hanging off the carbon, right? Yes, drawing the mirror image and like trying to superimpose it, or putting the model together, trying to superimpose it is fine, but on an exam, just like looking at a carbon, is it chiral? You need to see 4 different groups attached to the carbon. Because if you have the 2 of the same thing attached to that carbon, then you get more options of like rotating it, and you can wind up superimposing it onto itself. So a molecule's chiral if you have at least one carbon chiral atom. So only one makes you chiral, just like one double bond makes you an alkene. The carbon atom has to be bonded to 4 different groups. That's how you can tell a chiral carbon. And the whole molecule has non-superimposable mirror images. So if you took the mirror image of that molecule, you can't superimpose it. Again, check out that Khan Academy video on Canvas. It's really good. He actually uses a mirror and like a model kit to like explain it to you. It's a very good video. You could also get a model kit, stand in front of a mirror, and like try it yourself. So here's kind of what this model is talking about. So here's your mirror, and here's my molecule. This is the mirror image of this molecule. And so there's no way that I can rotate this mirror image and have it be the same. And you're like, yes, but I can just move this over here and it will look exactly the same as this. But it won't, because now these that are coming forward at you will be going back into the wall. And so remember that tetrahedron has a piece that's coming out and a piece that's going back. And so you rotate that around and you change those, and they're not going to be the same. So like the palm side is still facing down and the other palm side is still facing up. It's hard to see in images. So I really encourage you to like go grab a model kit, sit in front of a mirror, and then do it, or at least watch the video of someone else doing it. If you have 2 stereoisomers, okay, that cannot be superimposed, they're chiral, we call them enantiomers. So then there's a lot of words, so just kind of pause and write down the words and the definitions of them. So stereoisomers that cannot be superimposed are called enantiomers. If you have an achiral carbon atom, so you can see here that if you rotate that mirror image, it actually just is the same as the beginning. You can superimpose it. So that's just achiral. We do not call them anything. They're just the same thing. So they don't have a special name. So why don't we try looking at these carbons, looking at these compounds as saying they're chiral or achiral. So pause, give it a shot. All right. So looking at this carbon here, let's see the groups around the carbon is really how you can tell, like by looking at a Lewis structure. And so if you have 4 different groups around that carbon, it's chiral, meaning it will have a stereoisomer, it will have an enantiomer. This carbon has, we'll just count these. This carbon has 1, 2, 3, 4 different groups. So each of these groups is different. So this one is chiral. So B, looking at this carbon, I have 1, 2, 3, but this is the same as 1. So there's 2 H's, right? You don't have 4 different groups. You only have 3 different groups around the carbon. So this is achiral. This carbon has 1, 2, 3, 4 different groups, so we got another chiral. What about this carbon, the CH2 carbon? Automatically, if you got 2 H's, you can't be chiral. Yeah, what about this carbon? 3 H's, can't be chiral. And so you can kind of tell that your carbons, they typically, what they'll do when we're doing like things with saccharides is we'll have the achiral carbons kind of bunched together in a condensed structure, and then the chiral carbons will actually kind of draw out a longer structure for it because they're the ones that are a little bit more important in the structure, in like how to figure out the names and stuff. So a Fischer projection is a two-dimensional way to represent something in 3 dimensions. And we have to do this a lot in chemistry because molecules are 3-dimensional and we are usually writing them down on paper, which is 2-dimensional. And so Fischer came up with this method because he was tired of drawing all of these. You can't just draw like a bond line formula and show chirality, right? It's like I can't just draw this because none of these carbons are chiral. And so even if I have a carbon like this, well, this carbon now, if I have a methyl group and a chlorine group, well, this is another methyl group, so that doesn't count. Let's do this right here. So this carbon now is chiral because it has 4 different groups, a methyl, a chlorine, this ethyl group hanging off, and then a 1, 2, 3 propyl group on this side. This carbon has 4 different things on either side, but I can't tell which enantiomer it is because I don't know if this is coming into the board or out of the board or kind of which way it's going. And that really matters because the 2 different enantiomers have 2 different properties and you have to be able to tell the difference. And so we have to ditch this line angle formula when we're dealing with chiral molecules because it doesn't really help us identify the difference between the 2 chiral, the mirror image or the real one. And so what they were having to draw were these like wedges and dashes and a bunch of different kinds of ways. And so Fischer said, that's not succinct enough for me. I want to draw a different kind of thing, and it's going to help me because I'm drawing these all day and doing all the kinds of these reactions with them. And so we put the most highly oxidized carbon group at the top. What does that mean, highly oxidized carbon? It's the carbon with the most bonds to oxygen. Right? It's the most oxidized, because oxidized means if you're going to oxidize something, you add bonds to hydrogen. So the most oxidized is the carbon that's got the most bonds to oxygen. Vertical lines go back into the table, or into the board, whatever you're looking at. So here you would have your dash line. This is going to be a vertical line. A vertical is up and down. And then you would have your wedge is going to be a horizontal line. And horizontal lines go this way, right? And so it looks like this. So if you have your wedge dash, and this is a strange wedge dash, this wedge dash is gotten from taking a more traditional tetrahedron shape and opening it like a book. Again, I have a video that I posted on Canvas that will help you with this. Don't necessarily watch the whole thing, but just the beginning can really help you understand like how they're going from this to this. You do not need to go from this to this. You just need to be able to read this, okay? And understand what it is that I'm showing you. What I'm showing you here is that these lines, these horizontal lines, are going into the screen, and these lines are coming out into the space where you are. And so these are going back into the screen, these are coming out. So kind of like, think about it kind of like bending paper around each carbon. And so these are your wedge dash model turned into a Fischer projection. We have this glyceraldehyde. Okay, so it's got an aldehyde here, and it's a glycerol group. We've got this carbon is chiral because it has this group is different than this group, is different than this group, is different than this group, 4 different groups around it. Here's the mirror image, right? And there's no way I can put this on top of this and it be exactly the same. And so we've got L glyceraldehyde, and we'll talk about where we get this L from. It has to do with where this OH is. And we have D glyceraldehyde. These are enantiomers of each other. And L glyceraldehyde has different properties than D glyceraldehyde. And so this one may do something in my body, but this one is inactive. So I'm not sure if that's true or not. It just depends on which enantiomer you are. So it does matter. These little tiny changes, especially when we're talking about interacting with really delicate proteins and cell membranes in our body. So here's that D and L notation. You look at the hydroxyl group farthest away from the carbonyl carbon on the last chiral carbon. And so here's your carbonyl carbon. Find the last the carbon that's farthest away that's still chiral. This carbon here is not chiral because it's got two H's attached to it, right? So it's not a chiral carbon. And you can see that if it's not a chiral carbon, we'll typically just kind of put it in a condensed structure down here and not actually show it out, because we only are going to be showing our chiral carbons with our Fischer projection. So you've got your aldehyde group, and then the farthest chiral carbon is this carbon right here. So carbon number 3 is our farthest chiral carbon. And the OH is on the left side. And so I call it L enantiomer. So it is L erythros. Looking at this one, same compound, but this is the mirror image, yeah? So if you were to pretend like a mirror is right here, this is your mirror image. You get your H's. Right? So if you imagine your mirror here, what if your H is on the right side, now they're on the left side. Your OH is on the left side, now they're on the right side. If your OH that's on the chiral carbon farthest away from the carbonyl is on the right side, we call it the D isomer. Now, make a quick note of what the aldehyde does. The aldehyde is around a single bond. It can be rotated, but we don't change the direction of the oxygen. We always typically will put the oxygen out to the right. So you're looking at this as a mirror image. It's only the chiral carbons, it's only these here, that have 4 different groups. The carbonyl carbon can't be chiral because it doesn't have 4 different groups, because it only has 3 different groups attached to it. So you're only looking at these carbons here for chirality. So they're the only ones that really matter about the mirror image. So don't worry about your aldehyde or your other groups on here being mirror image. Just kind of copy them over, and only the ones in the middle of the projection are actually going to do the whole mirror image thing. So go ahead and see if you can figure out if the 2 in the pair are a mirror image that cannot be superimposed. So would you call them enantiomers? So give a pause and try it out. And so these 2, putting a mirror image here, I see my CH on the left, my H on the right, okay. Again, don't really worry about the order of these as actually being mirrored. Like, you don't need to like make this like this to be mirror. This is not a chiral carbon. Is this a chiral carbon? So this carbon has 1, 2, 3, 4 groups around it. So these are mirror images if this one has the same 4 groups around it, but in a different order, right? So yes, these are enantiomers. When I say different order, I mean, like, if you were to count clockwise around the compound, you would actually count, and we're not going to get into this, but it's something called R and S, enantiomers. And you start with the group that has highest priority, and you start counting clockwise. And so, if I were to count this, like, so let's just, not getting into all of that, but just assuming that I've got, this bromine is number 1, and I've got 2, or this one would be, it's different. I'm not going to get into it. So 3, 4, like, if I were to count this way, 1, 2, 3, 4, right? If you were just looking at like counting in that direction, do you have different things on different numbers? You do. So those would be enantiomers, right? So like, I know that if I were to just kind of look in this direction, this counterclockwise direction, I have different stuff at the 2nd and 4th place if I start from the bottom. And if you wanted to do clockwise around, you can find that too. So that's another way to make sure that they are enantiomers, that they do have the same stuff on them, right? Wouldn't call them structural isomers, but we would call them enantiomers because they're stereoisomers. They're mirror images that cannot be superimposed. So looking at these two down here, first, they're not chiral. This is not a chiral carbon because it has 2 H's. And so if it's achiral, they can't be enantiomers. So not enantiomers because achiral. And so don't even let it live. If it's not chiral, it just like can't be. So look at these Fischer projections. We're going to tell me if this is an L or D isomer. So give a pause and check it out. Alright, so looking at this thing, I got these aldehydes here, and we can look at this, and we can see that I have chiral carbons, and typically Fischer projections will always have your chiral carbons hanging out in this bone, like spine type thing. And just doing through a quick check to make sure that they're all chiral. They are all chiral, because if you look at these groups, right, this is like a ethyl aldehyde group, and this is a propyl butyl alcohol group here. The thing about this, the organic chemistry of like counting the chains, like kind of how you would count an ether on each side, right? You would kind of count like how many carbons are on each side. And they're also different because this chain ends in an aldehyde and this chain ends in an alcohol. So all of these carbons are going to be chiral. And so if you're looking at the chiral carbon, so this is the last chiral carbon, the farthest away from the carbonyl group. So our last chiral carbon is here, and okay, sorry about that. There might have been a little pause there, an interruption. So this guy is going to be D because he's on the right. So D stands for Latin for right, which is dexter. So if somebody's dexterous, you may think, oh, they use like their right and left hands, but dexter comes from the Latin for right. So looking at this guy, you've got your lowest or farthest away from the carbonyl group is still this carbon, but it's on the left side, so this would be the L enantiomer. So what I was talking about before, the reason why it's important to label these enantiomers, to have them, to know if there's something that is the same, that's a stereoisomer to what you're looking at, is that you have these very specific enzymes and receptors in your body that are very handed, right? They're chiral, and so they only will respond to molecules that fit exactly. And if it doesn't fit exactly in the right place, then it will not get accepted. And so if you have a protein that gets accidentally built in a wrong way and it won't wrap around the substrate in a certain way, like if it's an enzyme, then you get mutations and you get other physiological effects that happen downstream because of these things. So tiny changes in just like how a couple carbon atoms are arranged, or if a compound is the right mirror image of another compound, makes a big deal when we're talking about building up these really, really tiny molecules into tissues and organs and whole systems, right? And so typically one enantiomer, like the L isomer, will be the active one, and then the D one would be the inactive one, or vice versa. So it like wouldn't work. And so if you're talking about like medications or something too, sometimes you get the stereoisomers in medication making where one is doing one thing and the other is doing something else, or the other is just not active at all. And so that's why we have like active ingredients, I think, a lot in things. So here's kind of an image showing you this. Like if this is your enzyme service and you're trying to put this compound in the enzyme, the substrate in the enzyme, then this one will fit, but this one won't fit. And so these two are mirror images. We see this mirror coming down. We get these mirror images here. So these two are, it's a chiral carbon. It's got 4 things on either side. We'll get this mirror image going on. And so these are enantiomers of each other, and one will fit, the other won't fit. So it's kind of a good image for you to have in your head as to the importance of learning this. So as an example, we treat Parkinson's disease with L-DOPA. So there's your L, and that means that you've got that OH group on the left side when you're looking at a Fischer projection, and it's converted to dopamine. But D-dopa doesn't help with Parkinson's. It doesn't not convert it into dopamine, and so the brain is not releasing any extra serotonin. So if you're looking here, we're highlighting, sorry for that car going by, it's really loud, highlighting our chiral carbon here so you can see the differences, right? It looks exactly the same, right? It looks like you could just like, bloop, turn it around on each other, but you can't because this guy, these guys are all in a different, these are in a different order if you were to like count them around. These are mirror images of each other. Like I was saying before, only one of the enantiomer is actually biologically active or does the thing that you want it to do in the drugs. And then drugs have been produced that are mixtures. They use now technology to try to separate these mixtures, but if you have a mixture of enantiomers, you call it a racemic mixture. You may see that word around. You don't need to know it for your exam, but you may see it before you're done with all of this stuff, or if you get into the workplace. So a racemic mixture is like a mixture of enantiomers, like L and D enantiomers that are really hard to separate. And so we actually have to do we've developed technology to help us only produce one enantiomer at a time, or separate out enantiomers. So, we're going to get into looking at some monosaccharides. You need to know 3 monosaccharides. We got glucose, galactose, and fructose. They're most important of the monosaccharides, so please know those. These are all D. These are all D enantiomers, and so you do have L-glucose, L-galactose, and L-fructose, but the ones that are going to be doing stuff are the D versions. We can see that OH on the right side giving us that that dexter. Over here, you've got glucose, which is an aldehyde, so it's an aldo. You got galactose, also an aldo, and you got fructose, which is a keto. Here, if you look, just look for the differences, right? So you need to be able to recognize a Fischer projection in which one of these monosaccharides it is. And so if you know, you need to know that glucose and galactose, so both of my G's are aldehydes, or aldos. And my fructose is a keto. And then the fructose is pretty easy to recognize if you can see that ketone there. You know, if I'm talking about a monosaccharide and you see a ketone, it is fructose. But between glucose and galactose, it's really similar. So look at carbon 2, the same. Carbon 3, the same, superimposable. But carbon 4 is where you get the difference. So the only difference in glucose and galactose, I'll highlight. Here's that mirror image. It only occurs in one of them. The other carbons are exactly the same. And so you could superimpose all of these carbons to these. And they're not stereoisomers. They're actually different compounds here because they have this different arrangement on carbon 4. So the only thing that's different about glucose and galactose is carbon 4. One of them has an OH on the right side and the other has an OH on the left side. And that makes them totally different things, which is crazy. That like something that small could make a big difference, but it does. And then you have fructose with its ketone over here being all different. Now fructose and glucose are the same, except for carbon 2 is a ketone for fructose and carbon 2 is a alcohol here. Again, going through Fischer projections one more time, we got chiral carbons at the intersection, we got most oxidized at the top, and we show the non-chiral carbons hanging at the bottom. Farthest is how we determine L and D. I don't know why the textbook has these again. But it's the same thing in the monosaccharide. So like don't overthink it. Here's a ribose, okay? Kind of like the sugar that's in ribonucleic acid, that's ribose. And you got your L and you got your D. We got our L, we got our D. And D-glucose is the one that you need to know. But these are actually mirror images of each other. So if you cut that mirror right down the middle there, you got those mirror images there. So check out mannose and tell me if it is L or D. So looking at mannose, I got over here on the right. It's pretty easy, right? This is D because it's on the right. We call that D mannose. So how many chiral centers, and then tell me if it is L or D. So I got 1, 2 chiral centers. My OH is on the left, so it's L. So here's some more information about glucose and fructose. Glucose, you know glucose, found in fruits, corn syrup, honey. Aldohexose, we already talked about that. Look, they have the same, look at this. They are not stereoisomers. What are they? They have the same formula, which means galactose also has the same formula. We are structural isomers because we are actually structurally different. Stereoisomers are structurally the same. They're just mirror images, right? If you're talking about D-glucose, we also call it dextrose. So you may have heard that before. It's a building block in sucrose, lactose, maltose, all the polysaccharides. Or a lot of them have glucose in them. Like cellulose has glucose in it and glycogen. Fructose is a ketohexose. It's the sweetest. It's also twice as sweet as sucrose. That's why fruits are so sweet. So glucose and fructose, here they are. We can see them next to each other. Obviously, one's an aldehyde and one's got a ketone group. Everything else about them is the same, though. If you were to look at these last, this last little section here is the same. And then you got galactose. So galactose is the same as glucose, except carbon number 4 is reversed. Again, it's a structural isomer to glucose and fructose. You need to be able to convert galactose into glucose, which means you have to break bonds, a chemical reaction, and if you can't do that, you can't make the glucose from galactose, and you actually have galactosemia. So, hyperglycemia would mean too much glucose. Hypoglycemia means not enough glucose. You got to have glucose for your brain to work. And so make sure that you're not starving your body of... I'm not talking about the sugar that you eat is sucrose, and that is a... that's not simple glucose, but you need glucose in order to survive. And so you have to have glucose in your body. You get hypoglycemia if you don't have glucose. And so diabetes can cause hyperglycemia, which is too much glucose, and then the insulin cannot break that down. And then hypoglycemic, if you ever have gone without food for a while, or felt that kind of weakness, dizziness if you haven't eaten, then you've maybe experienced a little hypoglycemia. But if you do not have if you have diabetes, then it is much more intense for sure. And so if you can remember what fructose looks like, see if you can draw fructose. If you get the D version, which is the common version that you need to know, the D version, then try to do the L version as the mirror image. So go ahead and pause and see if you can remember what fructose looks like. Alright, you ready? Check it out. Did you get it? This is fructose. We got that CH2OH on the top. And we got our ketone here. And then for D, we have OH, HH on the left, and HOH, on the right, and then you got your mirror image. If you get one, you get the other, just by looking at the mirror image of those chiral carbons. Everything else is exactly the same. Okay, you need to know fructose, you need to know glucose, you need to know galactose. So it may be helpful to know like what the top and bottom are, and then like just labeling down the side like OH, H, OH, or just knowing it across, okay? Knowing where your OHs is the best, because then the other side is H. So you can just go, on the left side you got carbon number 3. On the right side we got carbon number 4 and 5. So just remembering 3 is on the left and 4 and 5 are on the right, then that can help you know what fructose is. Just as an example, but just either way, you should definitely start looking into memorizing that. Now we're going to talk about Hayward structures. I'm not going to have you draw a Hayward structure from a Fischer projection, but you need to know where the Hayward structure comes from so that you're not unable to read it. You need to be able to read a Hayward structure, but you do not have to build a Hayward structure. So I'm going to show you how it's built so you can understand what it is. Hayward structure is showing you the most stable form of your sugars, okay? And so our glucose, our fructose, they don't actually exist in these lines. Now, Fischer projections are easy for us to identify them, to look at them and think about their reactivity, but they really are most stable in our bodies in these ring structures. And so drawing these ring structures, including chirality, can get really weird because drawing rings is already kind of hard, and then if you try to add in all the wedges and dashes, you get all kinds of crazy things. And so Hayworth came along with this idea that, like, look, if we turn the ring like sideways and look down it from this angle, like straight on, we'd be able to see that there are certain groups that show up on the bottom of the ring and certain groups that show up on the top of the ring, and that can help us tell the chirality, the L, the D, and something we're going to call alpha and beta in a minute. And so if you're looking here, this wedge is showing you that this side of the ring is coming out of the page at you, and then the rest of it's kind of going back into the page. And so we'll talk about this in class. It's kind of like if I hold up a sheet of paper, there's stuff on top of it. So the CH2OH, the H, this OH, actually let me just highlight. These are all the things that are on top of the ring. And these are the things that are on the bottom of the ring. And the O is, this O here, is actually inside of the ring. And so everything is pink is on top, blue is on the bottom. So hopefully you can kind of see that. So how do I make them? So you got your Fischer projection. We're going to knock it over, okay? And then we're going to be connecting this guy and this guy. So we're going to be making a ring. So we're going to fold this carbon this way. So imagine that we're not like rotating it around, we're just kind of gonna fold it up so that this is now on the right and that this is gonna come down as I rotate it around. So we're just gonna kind of crank that over. Now, this OH is gonna attack this carbonyl carbon, because a carbonyl carbon is more positive because it's got this negative oxygen hanging out, and this oxygen is negative, so it's attracted to this carbonyl carbon. So these forces of attraction really are helping my sugars be stable. You get this negative oxygen, this positive carbonyl, and that's this attraction. Like, these things are not being put together by like invisible hands, they're just coming together naturally because of these attractive forces. And so you are going to cause this oxygen to bond with this carbon. This carbon is going to hang on to this oxygen, but it's going to turn this carbonyl group into an OH, into an alcohol. So we're going to kind of reduce it down. And so we have two ways of discerning which way this reaction kind of happened. If you wind up with the OH on the bottom, we call it alpha. If you wind up with the OH on top, we call it beta. And so you'll see that only a trace amount of glucose actually exists as open chain, where 36% of it has an alpha conformation and 64% has a beta conformation, with this oxygen, the OH on the oxygen side right here, this is your important part, is on the top. So beta on the top, alpha on the bottom. And so you can have your cyclic structures open and close, and again, you've got different amounts of them being opened or closed in different conformations. So looking at fructose, so fructose, we don't have quite as many carbons in here because we have these achiral carbon groups on the outside, so we get this pentane type ring here. We're still going to be looking at this. So here's the oxygen in the ring that's being made. We're still going to be looking at the OH on the second carbon. So we start with to the right of the oxygen is carbon 1. And so carbon 2, this is carbon 1, so carbon 2, right? We're building this down. Carbon 2 has an OH on the bottom, so we call it alpha. This carbon 2 has an OH on the top, so we call it beta. You can try it if you want to. You do not have to do this on an exam. You just need to be able to recognize it. So if you want to try it, you can. Here's what galactose looks like. So if we turn it over, knock it down, you're always going to have your carbon number 1 as your carbonyl carbon, or the one above the carbonyl carbon if you're talking about the ketone version. Take that OH, knock out that carbonyl, make it an alcohol. So you should get 2 conformations. We get alpha with the OH in the bottom, and you get beta with the OH on top. Again, you do not have to worry about drawing these from scratch. I will have them for you and just ask you, like, oh, is it alpha or beta? And you look at the OH that's to the right of the O, of the ether-looking group. So these chemical properties, I'm not going to have you memorize these chemical reactions. It is interesting if you want to look at it. Here's D-sorbitol in your gum. Monosaccharides can be used in Benedict solution. You've seen that before. Okay, we can reduce that down. You can make sugar acids. You can oxidize a ketone in a basic Benedict solution. You can convert fructose back to glucose. Here's that reaction. Kind of rearranges itself. You can reduce them by adding hydrogen, a platinum catalyst. These reactions should seem similar to you. I'm not going to have you go through them. You don't have to know what is going on. But like reducing would be getting rid of this bond to oxygen, making an alcohol, yeah? So reducing these sugars is how we get these sorbitols, xylose. So sugar-free things have these like reduced sugars in them. Again, you can practice this if you want to. Try to figure out what it's going to do. Essentially, you're just reducing an aldehyde, right? So reducing an aldehyde back into an alcohol, but I'm not going to ask you to do that on the exam. Right? So you should be reducing your aldehyde into an alcohol. And we change it to all mannitol, so mannose becomes mannitol. Glucose testing might be of interest to you, so we're going to look at that. Again, you don't have to know this for the exams involving the chemical reactions. So we're making gluconic acid by oxidizing our aldehyde into a carboxylic acid, yeah. And here's a chart of different glucose oxidase test results. You notice those units, that's a mass volume percent, right? So you could use that as a conversion factor, and this is milligram per deciliter, right? That's a density. You could use that as a conversion factor as well. Alright, getting back to the stuff you need to know. Disaccharide. Disaccharides contain all the monosaccharides, but only 2 of them at a time. And so you got to know glucose, galactose, and fructose. You need to know what lactose is galactose and glucose. So lactose make the 2 G's together. And how do we put them together? Well, we take the OH and the H of opposite ends. Okay, so these are the 2, here's the oxygen in the ring, right? Draw them, have them drawn to where the oxygen in the ring is both on the right side, and then you're going to make a little cross linkage here, okay? And what carbon is this? This is carbon number 1. Whatever's to the right of that O is carbon 1. Unless you're talking about fructose, the carbon 1 is going to be the one up here. So carbon 1, and this is one that being carbon 4. So this is 1, 2, 3, 4. That's carbon 4. So it is a 1,4 glycosidic bond. And we're looking at, is this alpha or beta? So we can tell me what the bond is here, if this is alpha or beta. I'm just kind of reading these little numbers here. This isn't a beta because it's on top. And this is not it's not a carbon 1, so we don't care about if it's alpha or beta. So only carbon 1 gets the alpha beta name. So this is just the beta 1,4 glycosidic bond. Now this is an alpha, but it's not the thing reacting, so it's not going to be included in the name of the bond. All right, so moving a little deeper into that, making sure that you can see that. I'll come back to this. Yeah, here we go. So we can see this. So if we have something like maltose, we'll put these two together and we get this glycosidic bond. It comes from carbon 1 and carbon 4. Carbon 1 is now alpha, so this is an alpha 1,4 glycosidic bond. So you need to tell me if you have a carbon 1 in your glycosidic bond, if it's alpha or beta, essentially. All right, moving back up, what are the disaccharides you gotta know? You gotta know maltose, lactose, and sucrose. Glucose make maltose. Glucose, galactose make lactose. Here's your lactose. See right here? See that? Lactose. And then you got glucose and fructose make the sucrose. Now, if you notice that these reactions, when we're combining these together, what is that, an H and an OH? We're taking out, look at the other product, water. That's a dehydration. Okay. Maltose, malt sugar, if you ever had like a malt, like a milkshake, that's what it is. 2-glucose. So it's formed from using cereals, and it's obtained from the hydrolysis of starch. So think about potatoes. Again, it's a alpha on the bottom of carbon 1. So it's an alpha 1,4 glycosidic bond. And then maltose, if you look at the result, you look at the farthest right OH now, because this one doesn't have an OH on carbon 1. The only carbon 1 OH left is this guy. And so we call the whole thing alpha, because that hydroxyl's on the bottom. So here's our lactose. Lactose is also an alpha. See this little OH right here? It's the only carbon 1 OH, and so that's a lactose. And we get this 1,4 beta, because your OH is on top of carbon 1. Glycosidic bond. Now let's look at sucrose. So I wish they have bigger pictures here. The next one's a bigger picture. And so we get, when you're talking about sucrose, you want to put them on top of each other, the glucose and the fructose, because it's going to help you put the structure together. And so you're looking at these on top of each other, not next to the others. You want them to write them next to each other, like left and right, galactose and glucose. And then here you want to do glucose on top of fructose. To help you see the connection. So we get the OH from carbon number 1, and it is on the bottom, so it is alpha. And then you have, you're using the OH now on carbon number 2, which is the important carbon. It's the first chiral carbon of fructose, and so that is on top, it is a beta. So your glycosidic bond to make sucrose is actually alpha and beta, and it's carbon 1 and carbon 2, because the first chiral carbon you run into, it matters where that OH is. And so your fructose is the beta with it on top, and your glucose is the one on the bottom. So you got some different sweeteners. And here you can look at the sweeteners, how sweet they are. A lot of non-carbohydrate sweeteners are actually way sweeter than your simple sugars. So here's some more glycosidic bonds here, right? See those? We got aspartame. So you can do a quick check and tell me the monosaccharides in each. So you're going to pick 2. So remember, lactose comes from what? Here are your answers. Glucose and galactose. Maltose is just 2 glucoses. Sucrose is glucose and fructose. And you can also remember the alpha and beta if you want to, and it'll help you figure out what linkages you're going to be using. Alright, blood types. Now, hopefully you know maybe what blood type you are. You should definitely know that. Because if you are like me and you're type O, you can only ever get from other type O's. I cannot receive any blood from type A or type B. It will kill me. So, how is that? Why is that? Well, you've got these saccharides attached to your blood cells. Okay, they're called terminal saccharides. And type O has 3 of these terminal saccharides. It's got the N-acetylglucosamine, glucosamine. It's got galactose, right? And it's got fucose. Right, so type O has these 3. And actually, look at type A. It also has those 3. And type B also has those 3. So type O is called the universal donor, meaning that type O can go into type A, and type A will not get hurt. And type B can also take on type O and it will not get hurt because it has the same parts. So O has all the same parts as A and B, so O is a universal donor. Now, if O were to take on A's blood, so if you were type O and you were to get a transfusion with A, you'd have this N-acetylgalactosamine that you don't know what to do with. And it's not here. And so these blood cells would be looked at as foreign in your body, and your body would attack them. Same thing with the type B. You got this extra galactose here. I don't know what that is if I'm type O, and my blood cells will be attacking these type B and type A blood cells. Actually, if you're a woman who is type O and you're pregnant with a baby that's a different type, you have to be very careful, and you have to get injections to make sure your body doesn't reject the baby's blood type, right? So blood typing is really interesting. And if you are AB, I think that you are the universal acceptor. You can get any because you can get either A or B because you've got a mixture of both, and then everybody gets O. So this is just going over everything that we just talked about. And so here are the little groups that are hanging off the blood if we want to look at their chemical structures. N-acetyl means you got an acetyl group hanging off your N because it's an amine, glucosamine and galactosamine. Alright, here's a quick learning check. Pause and see if you can figure out these glycosidic bonds. So what are the monosaccharide units in Melibos? It's 30 times sweeter than sucrose. So if you're looking at these, we got galactose and glucose. And you should be able to recognize that fourth carbon that's different, right? So these look exactly the same. So we should be thinking, okay, either it's both galactose or both glucose. Definitely not fructose. We don't have that that pentane looking ring. So we're going to look for carbon 4 to find our difference. We got 1, 2, 3, 4. 1, 2, 3, 4. Alright, this one has an OH on the top and OH on the bottom. These are different. One is glucose, one is galactose. Now, I have carbon 6, right? This is 5, this is 6, bonded with carbon 1 here. And if I'm bonded with it on the bottom, was it alpha or beta? Right, it was beta. And so this is a beta 1,6 glycosidic bond. And now, is the structure alpha or beta? So looking at its only carbon number 1, it's on the bottom. It is beta. Or sorry, alpha on the bottom. Yes, alpha. All right. Polysaccharides are many saccharides, so many sugars linked together. Again, you get those glycosidic bonds. I would focus on mainly here on like memorizing the different monosaccharides, disaccharides, and then looking at how to tell those glycosidic bonds from Hayward's projection. So focus most of your practice there. So this is cellulose. So cellulose is all glucose connected with beta 1,4 glycosidic bonds. And cellulose is in plants, right? So here is glucose again, Hayward, kind of like a little mini Haworth projection without the wedge. All polymers of glucose, amylopectin, cellulose, amylose. So these are all just long, different chains of glucose. And they all have different glycosidic bonds. So here in amylose, you've got an unbranched chain with the 1,4 glycosidic bond. If you get a branched chain, you get a little bit different, the 1,6 over on the right. And that's in amylopectin. You get amylose in potatoes. 20% of starch. And you get amylopectin in potatoes as well. And I'm not going to ask you, what do you get from potatoes? Like, just know that they're things. Glycogen is another polymer of glucose. And information about cellulose. It gives the cell walls its rigidity. And the picture of cellulose. You don't have to worry about this learning check unless you really want to. Alright, and that is the end. So with carbohydrates, you need to memorize your monosaccharides. So we need to memorize our glucose, galactose, and fructose. Remember the D versions of them. You can tell me the L's if you want. You need to know what a chiral compound is, how to tell a chiral compound. You need to be able to read a Fischer projection, like tell me L or D, and you need to be able to read a Haworth structure, telling me alpha, beta, and looking at those glycosidic bonds. But you do not need to be able to straight up draw Fischer projections from Lewis structures, and you don't have to draw Haworth structures from Fischer projections. Unless you really want to go crazy and learn it, you can, but you don't have to for my exam. You need to know 3 disaccharides, maltose, lactose, and sucrose, and you need to know what monosaccharides make them up. You've got 3 polysaccharides that you need to know maybe the names of, but I'm not going to get really specific, like, well, which one is this in? Amylose, amylopectin, cellulose, and glycogen, they're all polymers of glucose, okay? And it's just different. I'm not going to ask you how many chains of glucose is in each. You need to know that you probably should know that glycogen is in animals if you're going into healthcare, and that cellulose is in plants. Right? And amylose and amylopectin are also in starches. So yeah, so definitely we're picking and choosing a little bit from this chapter. Let me know if you're not sure if something is going to be covered or not.